Welcome to this explainer. Look, if you're an IT support engineer, you have absolutely felt the heat of a high priority ticket where a user is complaining that an application is just painfully slow. Well, today I'm taking you on a bit of a DBA ride along. We're going to demystify those slow queries and show you exactly how to hunt down the root cause using MySQL Workbench's Visual Explain feature. We're going to turn that guessing game into a targeted, guaranteed fix. Here's a quick look at our roadmap. First, we'll cover the slow query problem. Second, running Visual Explain. Third, decoding the execution plan. Fourth, identifying table scans. And finally, number 5, a real scenario involving a search timeout. All right, let's jump right into section 1, the slow query problem. You know the drill, those dreaded database escalations. It's the ultimate question that every slow application ticket boils down to, right? Your query is slow, but why? I mean, is the server running out of CPU? Are we waiting on disk I/O? The truth is, behind almost every sluggish application is a database query that's just executing horribly inefficiently. The database engine is literally working way too hard to find the data you asked for. To ground this, let's look at a totally realistic, high-pressure support ticket. User reports the Sequila movie search page is timing out. Ouch. By the way, the Sequila database is just a standard sample database we're using for our local MySQL 8 demo environment today. But a timeout? That means the query took so long that the application just threw its hands up and gave up. It's our job to figure out what MySQL is doing behind the scenes to cause that massive delay. Moving right along to section 2, running Visual Explain in MySQL Workbench 8.x. So generating a visual execution plan is actually incredibly straightforward. Step 1, you just open your SQL editor in MySQL Workbench and connect to your database. Step 2, write out the exact select query the application is trying to run. And step 3, this is the magic part, just look at the toolbar for the magnifying glass icon with a little lightning bolt. Clicking that runs the explain current statement command, and it instantly translates all that raw tabular query data into a really beautiful color-coded flowchart. Just a quick note here. While explain can be used on other statements, these visual explain diagrams really shine the brightest when you're analyzing select statements. They give us a direct window into the MySQL cost-based optimizer. Think of the optimizer as the database's brain. It evaluates multiple ways to execute your query, factoring in things like CPU, memory, and disk I/O, and chooses what it thinks is the most efficient flow. We're essentially getting to look at the database's inner thought process. Okay, section 3, decoding the execution plan. Let's learn how to read these visual cues. Visual Explain basically gives you a heat map to spot bottlenecks. Every operation becomes a node, and they are color-coded by cost. Blue and green nodes? Totally fine. They mean normal, fast costs, usually a nice, efficient index lookup. Yellow nodes mean you've got an elevated cost. But those red nodes? No way. That's your problem. A red node means that single operation is eating up over 80% of the total query cost. When you see red, you've found your primary target for optimization. But wait, what do we actually mean by cost? Well, a cost estimate is a calculated metric based on the I/O and CPU power needed to fetch the data. The optimizer assigns a cost to every possible execution path. Actually, scratch that. It evaluates the paths and just picks the absolutely cheapest one. That color-coded gauge on your node, it's showing you that specific operation's relative percentage of the total workload. If a node is consuming a huge chunk of the cost, that is exactly where the engine is struggling. Right alongside cost, we have row estimates. This is the expected number of rows the database thinks it needs to examine to find your data. Now pay close attention to this, because it's huge. One of the biggest red flags for a bad query is a massive discrepancy between the rows examined and the actual rows sent back to the user. I mean, if your query has to examine 1,000,000 rows just to return 10, you've got a massive inefficiency on your hands.
Which brings us to section 4, identifying table scans, the absolute performance villain.
If there is only one single thing you take away from this explainer, let it be this. Beware the full table scan. When you're looking at your Visual Explain node, check the access type field. If it says all, you've found your culprit. An access type of all means MySQL literally had to check every single row in the entire table. It's like trying to find a specific book in a giant library, but instead of using the catalog system, you're forced to walk down every aisle and check every single book on every single shelf, one by one. It's brutal. To put that into perspective, check out this number from our source data: 635,310 rows.
In one of the benchmark examples, MySQL had to scan through over 600,000 unindexed rows just to find one single record. That's insane. If your dataset is bigger than your system's memory, pulling all those rows from the disk is going to cause massive I/O pressure and completely spike your CPU.
All right, section 5, let's bring it all back to our real scenario, solving that Sequila search timeout issue. So we run the timeout query through Visual Explain, and boom, we get this glaring red node. Let's break down the data inside it. The table is orders. The access type is all. There's our villain, the full table scan. The estimated rows examined is 1.5 million. And critically, look at the key field. It says null. This is the smoking gun. It proves MySQL is not using an index to filter this data. That missing index on the user's search column is exactly what's causing the application to time out. So how do we fix it? Here's the DBA playbook. Step 1, we've already done. Identify the slow operation, which was our red full table scan node. Step 2 is the fix. We simply add an index to the column being filtered in the query's where clause. This gives MySQL.library catalog it so desperately needs. And step 3, never skip this. We verify the fix by running Visual Explain one more time. And check out this before and after. It's like night and day. Before we added the index, we had a red node, an access type of all, a null key, and a brutal execution time of 11 seconds. After adding the index, the node turns a nice healthy green. The access type changes to ref, which means it's doing an efficient index lookup. It actually lists the index it used in the key field. And the execution time, it drops to a lightning-fast 0.01 seconds. We just solved the whole shebang. So, let's summarize your ultimate DBA ride-along takeaways. Next time a slow application ticket lands in your queue, load up MySQL Workbench. Spot those red nodes in the heat map. Check them for an access type of all, because that means a full table scan. Look for a massive discrepancy in row estimates compared to what's actually returned. And finally, work with your dev team to add indexes to those heavily filtered columns. You've got the tools now to see exactly how your database is thinking. So I'm going to leave you with this. What other slow queries in your system right now are secretly hiding a missing index? Go fire up Visual Explain, hunt down those red nodes, and turn them green. Thanks for joining me on this explainer, and happy optimizing.